What we're going to look at now is the principle behind the electric generator. It comes from the idea that this EMF can be induced by a changing magnetic field. In other words, the magnetic field which is linked by a coil, if that is changing, then we can induce an EMF, induce a voltage, and from that we can produce AC current, AC voltage. This is the basic principle, that we have a magnetic field here, we have a coil which is placed inside the magnetic field, and basically because it's at 90 degrees to this, it is catching a large amount of magnetic field. So the amount of flux that's linked here is at a maximum. Okay, the cosine theta. Theta is the angle between the normal and the magnetic field, which is a very small value at the moment, so it's a cosine of 0. So in other words, we have a maximum flux linkage at the moment. Then what's going to happen is that this coil is going to rotate round. As it changes round, as it rotates round, the amount of flux linkage will change. This change of flux linkage we know will induce an EMF. And this is what we're going to look at in the next slide. So here we have different phases as this rotates round. And we're going to look at the EMF that is induced at different times. Now let's take the first point here. Here we know the flux is at a maximum. Okay, so the flux is a maximum value there. Then the flux, as the coil starts to move over, the flux gets less because it's presented with a smaller area, because this plane is changing orientation. Here, the amount of flux that is linked by this coil is 0, because the plane of the coil is parallel to the field lines. There are no field lines that will be cutting through this magnetic field, so it will be 0. The flux linkage is 0. So we go on like this. This is when the flux linkage is a maximum, but the coil has flipped over, so the EMF will be in the other direction. So we write this as a negative sign here. Then it rotates. Here again, the plane of the coil is parallel to the field lines, and therefore the flux linkage will be 0. This is not cutting through any of the flux. So we basically have a sinusoidal pattern there, and this just shows the flux which is linked by the coil. Now we're going to look at the EMF. Remember that the EMF depends on the number of turns. In this case, it's 1 turn. It depends on the rate that the flux is changing with respect to time. This is a flux time graph. So in other words, it's going to be the gradient of this graph here. At which rate is this changing? Well, we know the flux is a maximum, but the gradient is 0. It's changing. The flux linkage is changing at the smallest amount at that point. So the EMF will be 0 at that point. Then it starts to change, so it starts to increase here. At this point, even though the flux is 0, it's the point when it's changing from one side of the coil to the other side. This is when the flux linkage is changing the most. And you can see that because the gradient of this graph here will be changing the most then. So that's when the EMF will be a maximum. And then it starts to go to 0 again. Here we have a maximum flux linkage again. The EMF here will be 0, because even though the flux is at the maximum, it's actually changing at the smallest rate. And we know the gradient here is 0. And so on. So this is basically the pattern that we get. Notice that the gradient of this graph here is negative, and this is a positive value. But this is correct because the gradient of this graph is negative, and we have to multiply by -1 anyway, so the EMF will be positive. This is why the negative gradient gives a positive EMF. Remember Lenz's law, that the direction of the EMF will always produce a magnetic field which will oppose the change that is producing it. So this is one example here. this is the full picture. We have the magnetic field lines going downwards. At this point, the flux linkage is next to zero, next to nothing, but it's changing at the greatest rate. So this is why this is a maximum EMF. In fact, we're at this point here. This is when the flux linkage is a maximum. But if it's the flux linkage is a maximum, it's actually not changing very much. It's got to the peak value for the flux linkage, but the EMF is going to be zero. So this is why this is zero. So this one side is connected to one ring, the other one is connected to the other ring. Here we have again the same thing again. This is what a generator is. It's a coil of wire which is inside a magnetic field. One is connected by these brushes which touch these rings, these slip rings, and they enable you to pick up the induced EMF there. At this point, this is when the plane of the coil is parallel to the magnetic field. So it is when it's changing, the flux is changing the most, because the flux linkage here is zero. The rate of change of flux is a maximum. So this is when you're going to get a maximum EMF. So that would be, for example, here. The magnetic field lines are going from left to right, and this is parallel to then, in other words, 90 degrees. So it's cosine of 90. So the EMF will be a maximum there. At this point, and at this point, this is when the field cut, the field linked by the coil is at a maximum, and that's when the EMF is actually zero, because even though the amount of magnetic field which is being cut by the coil is at a maximum, it's actually changing at the smallest rate, zero, when it gets to exactly this point. So this should be a sinusoidal pattern here, which means a sine curve. Okay, so what does this EMF depend on? We know it depends on N. It depends on the rate of flux linkage, the rate of change of flux. So it depends on the number of turns of the coil, which is not actually in this equation. For every link, you're going to get another amount of EMF. The strength of the magnetic field, because this is the flux is equal to BA. So if you have a larger B, you get a larger flux. The speed at which the coil or magnetic field rotates. The speed means how quickly it rotates. If it rotates twice as quickly, you're going to get a higher frequency, and you're also going to get a larger EMF. We have to explain the operation of a basic AC generator. So I'll show you this applet at the end. The coil rotates in a magnetic field, and because it rotates, the flux linkage changes. As the changing flux will induce an EMF in the coil. When the coil reverses and goes on the other side, the changing flux induces an EMF again, but in the opposite direction. This is an interesting thing. If you rotate it twice as quickly, the rate of change of flux will be twice as much. We'll look at a Java applet. Okay, here we have the nice Java applet by Mr. Fent. So, can I pause this? Pause, yes. Here we have the maximum flux which is linked by the coil. The EMF is equal to 0. And there's the EMF. The U is given the EMF. This is the smallest value here. And notice what happens as it rotates. What happens to the EMF? This point when it's vertical, stop. That's when the EMF is at the maximum. Keep it rotating. That's where it's 0. So I want you, for 2 oscillations, look at what happens to the position of this and how the EMF changes. Maximum EMF. 0 EMF. Maximum. 0. Okay. You can see what happens to the oscillations here. Now what I'm going to do is increase the rate of rotation. So let's see what happens. We have 1, 2, 3 time periods here. If I increase the rate of rotation, we have now 1, 2, 3, 4, 5. We have 9 time periods, this is spinning faster, and the EMF is going to be a larger value because the flux is changing at a faster rate. Notice that the EMF has got a value which is much larger now. It should actually be many times larger, but it's only showing a twice an EMF. So notice when the EMF is 0, which is now, observe the position of the coil when the EMF is 0, i.e. now and now. Okay. I'll slow it down, see what happens to the size of the EMF. Gets smaller, the frequency changes, this slows down, the size of the EMF will be smaller as well. So there you have it.